Welcome everyone today. Thanks for joining us, and thanks for putting up with me in this presentation. And it's about kind of timber bridges, old timber bridges, restoration, inspection, design. It's a smattering. I thought I'd pull together for you that kind of focuses on timber bridges and the restoration thereof. And just kind of a little background on who I am and who I work for. Of course, WRD is a code certified test and third-party lab. And we have a commercial engineering wing, and we specialize in the inspection and the design of maintenance strategies or restoration for old timber bridges. And we have a commercial engineering wing that designs new timber bridges as well, like the one you see right here in front of you on the screen. And I'm just going to take a carbon plug for a minute. I'm not a tree hugger, but I am interested in carbon. And this bridge on the top replaced the bridge on the bottom. And the bridge on the bottom was steel. It was 48 years old. It had been built on a timber substructure that was 100 years when it was built on it. They drove some extra piles and put the steel bridge on it. And the steel bridge was in the highest exposed and embedded corrosion zone in Canada, close to Amherst, Nova Scotia, near Allac. And you can see the lower photo on the right shows what happens when you don't keep right after steel bridges in high embedded and corrosion zones. They fail and the bridge goes out of service. And the bridge on the top is the new one that I designed to replace it. It's a 3-lane, long 40-meter clear span in the middle. It's the longest 3-lane design timber bridge in Canada. And this bridge was designed to kind of look like the old one. The bridge is called the Rainbow Bridge, and it's built out of timber the whole bridge was completely machined and pre-assembled in a manufacturing facility, taken apart, treated, shipped to the site, reassembled on the old foundation. We reused the old foundation. And the number that I'm going to talk about in carbon right now is staggering. It had a minus 960 metric tons of sequestered carbon versus the cost in steel of in terms of carbon of reconstructing that steel bridge you see on the bottom left with 2,980 metric tons. So out of the gate, you can see why timber bridges, both old and new, are great ways to go carbon friendly and carry traffic across the gap. We were fortunate enough to win the Merit Award for that bridge just this past while in 2020. So where did I get my start? Well, I grew up in a little place down by Fundy National Park, the oldest national park in Canada. And it's on the Bay of Fundy in Eastern Canada. And I invite you all to come and see me. I have a summer home there still. I'm talking to you today from Jacksonville, Florida, where the head office is. And I work out of this office, but I have a home there still, just up the road from this bridge. And this bridge is called Sawmill Creek Covered Bridge. It was built in 1905, and the sign says, "Walk your horse or pay a fine." And this bridge was built by the old designers. It's a Howe truss covered in timber siding with a roof on it. Now, lots of people say, well, you know, why did they cover that bridge? Well, contrary to public opinion, they didn't cover the bridge to provide a place for the horses to get out of the rain, or to kiss their girlfriends, or to yell, "Echo." It had nothing to do with that. The cover on this bridge was designed by European designers way back hundreds of years ago. And they knew that if they covered up the connections in this timber bridge, that the timber bridge would last a long time. And it has. And many of them, like it in New Brunswick, have lasted a long time. And this bridge was designed at the turn of the century for 12 metric tons, roughly. And it was designed with wooden joints and wooden connectors and cast iron metal. And over the years, there'd been a lot of different types of repairs put on the bridge, not many of them good, because the art of building with wooden joinery has kind of been lost. And so the government decided that they didn't want to have the covered bridge there back in 1978, 1982. And so they had lost track of how to fix and build these bridges. So they built a concrete bridge beside it. This is it here. And this bridge has been out of service 3 times since 1982. And the covered bridge is still there. today. It's still in service today. They use it for a walking track. And so that tells us a story that covered bridges and timber bridges can last a long time, as timber structures can, if properly maintained and looked after. Well, that bridge gave me my interest and got me my start in this whole business of restoration of timber bridges and buildings. And I went to school pursuing that type of career. And I grew up here. As you can see, this is a picture of Eastern Canada, it's a map. And in the Bay of Fundy, we're known for some interesting things. And I'm going to show you this just because if you don't remember anything else about this presentation, maybe you'll remember this. This is Eastern Canada. This is New Brunswick. This is a St. John River. And I grew up right here at this point in Albert County by Fundy National Park. And we have something very unique that goes on in this area. It's the largest tides in the world. 14 meters plus, twice a day, come in and out of this bay. And I'm going to just show you this picture as I talk, because it's a unique little place in the world, because in this bay area, more water comes in twice a day than the combined flow of all the freshwater rivers in the world. And as you can see here, this is a shot of the Rocks, or the park. It's called the Rocks. And you can see the tide coming in here and people kayaking around. And it's about a half a mile from my home. And you can see the amount of water going in and out twice a day. And as a kid, I used to play in the caves that it created. And it's an interesting little area in the world today. And so with that, you'll probably remember that, not much else about my presentation. So as I said, we're a code certified test and third-party agency. We specialize in wood. And just a little plug, we won the Charles Pankel Award for Structural Innovation in '96. And then in '97, we won the Nova Award, which is all construction products for work with high strength fiber reinforcement of wood and wood composites. And I don't say this to brag, it's just I say it because it shows that a jury of peers in my field have found what we have done bona fide. And I have a few patents, as Doug mentioned. I have over 40 patents in the area of high strength fiber and wood composites. And I developed this engineering passion because I really believe in the restoration of things. I like to restore timber stuff. As you can see here, pictures from Australia, where I had restored a timber bridge back many years ago. That was 100 years, 120 years at the time of the restoration. It's about 130 years now old. And you can see this bridge here, Kerwin's Bridge, which is in Australia too, is 360 meters long, a big dog leg in the middle, so they could pull the horse and wagon to the side to let others by. And, these old timber bridges, our communities want to keep them. And they're at juxtaposition today with lots of the local governments who own most of our timber bridges, because they want to replace them and put concrete ones in, and they don't like to have to deal with the old timber. And I'm constantly pushing these agencies to think about restoration on the design and supply of new timber bridges. So we test these products to obtain code approvals for people, timber bridge products and timber building products. And at our lab in Jefferson, we test full-scale beams. We can test some big ones, I'll tell you. Upwards of 25-meter clear span we can test in our big beam testers, where we break them. And this is an old railway trestle bridge that we were teaching students how to restore it after it had been broken. And piles, where we test piles. And we have species identification, where we have microscopy methods of using minute structure analysis to determine the species of wood, so that we can help people identify, for example, whether Douglas fir is coastal or inland, or what type of spotted gum it is in Australia, or what type of teak it is. Is the teak really coming from Burma, or is it coming from another location? Is it the same type of teak? For those folks listening to us from England right now, one of the projects we're working on is the identification of whether Turkish walnut is the same as English walnut in terms of making the Purdy firearms. If you're from England, you'll know about Purdy firearms. And they are going to take down what we call a MIEAust tree, and that tree will provide stock for them to make forearms and stocks for the next 25 or 30 years. And this tree will tell a story, and we help them identify the wood and test its strength and know whether it'll be right to use in firearms. So we look at these common features to identify it. We test for fire, the fire resistance rating in minutes of assemblies and elements, as you can see here, testing this assembly. And this testing of fire resistance of pieces with reinforcement. And so we develop high strength fibers. You can see here, this is Kevlar and carbon used to make reinforced polymers that can be used like rebar in different locations for wood to strengthen it. This product is 5 times the strength of steel at 1/5 the dead weight. It has a coefficient of thermal expansion about the same as wood, different from steel, which is 3 or 4 orders of magnitude more, and you can apply it to wood and strengthen it in many different forms. So like this piece here, this section is equal in strength to this section. It's made from low grade, use a piece of high strength fiber, and thus if we have an old building where there's a deterioration of elements, we can use fibers strategically placed to preserve them in place, carry the loads that are necessary, and if required, turn a public occupancy around so that you can put 100 pounds a square foot or 5 kPa versus 2. So WRD has evolved into in situ inspection and destructive testing as well to identify capacities, as you can see here, testing piles and developing ways of wrapping existing piles and columns to basically increase their capacity in situ, testing them to failure, as you can see here, injections. We offer training courses, as you can see, webinars. We have 16 different training courses that we offer to people to teach timber bridge inspection and maintenance, for example, and advanced design of timber structures. If any are familiar with the Blue Nose, it's on the Canadian dime. And we developed a restoration for the Blue Nose, where the Blue Nose was built, the boat building down in Lunenburg, Nova Scotia. Or this guy here, which is out in the prairies in Saskatoon. And this guy here in Australia, where we test spotted gum. And what we do with these training courses is really pass on knowledge about timber. And that's what it's all about, is leaving behind a legacy for those who want to continue this process of preserving and extending the life of timber. This is from Brisbane, Australia, testing, taking piles to failure and teaching students how to restore them, as you can see here in the teaching slides. South Africa, Paul Matthews, South Africa, I have a bridge in Cape Town this year yet to restore, design a restoration for. So these sorts of things involve the restoration and extension of life for diffusers, for example. This is a diffuser. You know, there's 3 ways to preserve wood: preservatives, fumigants, and diffusers. And diffusers are naturally occurring salts that are non-toxic, that brine when the moisture content hits 22%, the point at which wood will start to decay. And it allows us to basically put protection inside wood to extend its life. Or use these non-destructive test methods like stress wave timers, where we send a compression wave through the wood to find lousy wood and cavities that are hidden from view. And to teach students how to do that in old covered bridges is a pretty important thing. And out they'll come with certificates like this, where they've been trained, and these certificates are IES certified, of course. So bridges come in many forms. This is a bridge in North Vietnam. It's a cable strung across the river. And each year, the students that are in a village have to get across to school on the other side of the river. There's no money to build a bridge, proper bridge, so they have a cable. They give the students a leather belt and a blue shirt, and they slide across the cable, drop into the water, get out and go to school. And each year they lose so many to the Crocs, but the cost of the bridge is worth more than the cost of a few children. That's not what we would think in the G10, but that's how it goes in North Vietnam. You see bridges like this, for example, are in Lima, Peru, where the chief, every year they have a festival, and the chief crawls across this hemp bridge, and he has a smaller string tied to him, and he pulls across a bigger one and a bigger one, and they cut the old bridge away and pull a new one into place, and that's called maintenance, where they replace the bridge every year. Or this one here, where the cattle and horses are using the bridge along with trucks and cars, because bridges are used by a host of different things to get across the gap. This bridge in Calgary is for the elk. It serves one purpose, just the elk. They were going across to Trans-Canada and getting hit, so they built this bridge for the elk. They put manure across the bridge, took a domesticated one across first, and now the elk are happy to use this bridge and stay off the highway. This bridge in the Pacific Highway in Australia, I went back and forth under 25 or 6 times before I realized that there's nothing on top of this bridge but trees. It was a $7.6 million structure, masonry structure, built across the Pacific Divided Highway with one sole purpose, and that was to get what? Koala bears across the highway. So bridges can be built for many different reasons, and they can be built to last a long time. This bridge built in northern India was grown, Fiscus benjamina. 600 years later, still in service. The people liked it so much, they grew a double-decker bridge. And they liked their double-decker bridge so much, they grew the handrails so that people could continue to get across the gap. And the reason these bridges lasted a long time is they grew their connectors. And instead of having a steel connector that went down from the top through the middle and let water into the center of the piece leading to decay, these connectors didn't follow that path. And this bridge here certainly lasts a long bridge in northern Japan. It's a leaf spring bridge, 565 years old. So there's nothing about timber bridges that says they can't last a long time. They can if they're built correctly. This shows you a picture. I'm a railway bridge enthusiast, and this bridge is built in the dead red center. It's called the Pitchy Witchy Railway Bridge. And there was 26 bridges underneath the tourist train that took from Adelaide up to the dead red center. And a local consultant who didn't know about timber came in, realized they were built in 1865, and immediately quarantined all the bridges and said they were done, that the bridge had reached the end of its used by date. So they brought me in. They knew that this was a specialty of mine. And I looked at all 26 bridges that were built with Jarrah wood and cast iron trusses and so on. And in the 22 bridges, I could not find one bad piece of wood. And I reinstated the bridges to go, and they're running tourist trains on it right now. And that's because it's old doesn't mean that it's no good. And the wood can last a long time and keep going on in service. You know, what bridge owners are really looking for is longevity. This is one of the 12 apostles, there's 11 now, in southern Australia. And they've been there for millions of years. And what our bridge owners want is to have our bridges there a long while. And in New Brunswick, we have an interesting situation in Eastern Canada, in that the longest covered bridge in the world is there in Heartland, New Brunswick, still in service today. And why is it still in service over 100 years later? Why is that? It's because the designers knew that if they built a cover over the bridge and kept the water off it, it would last a long time through all seasons, snow and rain and wind. This bridge up in West Grey in Ontario, not far from Doug, was built before the turn of the century. We're going to do that because it went away on me here. As you can see it here, it's one of the first videos in Canada, was a picture of the old CPR going across this bridge in Durham. And this old rail bridge had been in service a long, long time. You can see the grist mill across the bridge here. And I achieved this video because they asked me to come in and look at this bridge after the consultants had determined that it was time to take this bridge away. This is a before shot here. And I said to the council, I said, I don't know why we'd want to take this old bridge apart. I believe there's plenty of good left in this bridge. Why don't we restore it? And so they gave me the opportunity to do that. And we designed a restoration for the bridge and combined old and new elements to bring this bridge back to service. And it's back in service now. A much lower cost way of doing it, a fifth or a sixth the cost of new, and restored the history of the past for the people. These covered bridges represent the history of Eastern Canada, as you can see here in America. I'll just flip through some of them old, some of them new. This one here in Crooked Creek is on a road that's closed down right now, and it's 120 years old, and it sits in the middle of nowhere with a road that doesn't even connect to it anymore in New Brunswick. And so it continues to go on even though it hasn't been maintained. I see this Sawmill Parkway, the one I showed you earlier. Hammond River, Diggity Wash, interesting names for bridges, covered bridges, all with their own identity, all their own statement that they make to the community, and people's initials carved into them. And I sent around to you a little blurb before this presentation as a teaser. It was just out this month, the Atlantic Forestry Journal, of one that I'm going to talk about in a minute called Milkish Inlet, where the old initials that were carved into the sides of the webs, you know, talking about this guy loving this girl, are still there today. And wood in many of these bridges, that when they were built 120 years ago, the wood itself was then 200 years old. So you're talking about wood in these bridges that was well before 1700, still in service today, in these interesting bridges that represent the history of our past, as you can see here, from different places in America and in Canada. So what's happening with our covered bridges? Well, I'll tell you a little story about what's happening to them and why it's so important for us to be aware. This is the Hammond Road covered bridge that a few years back they discovered had some decay in places that they didn't know. And instead of pursuing the completion of the bridge after a major incident happened where they lost an excavator through the floor, they turned the bridge into taking it down and this. And that's the sad commentary about what's happening to our covered bridges all over the place because of a lack of knowledge on the part of designers, a lack of availability of craftsmanship to do the right stuff, the poor inspection practices that don't find bad actors until the bad actors have taken the bridge out totally. And that's what we're trying to prevent. You know, the seasons of time take our bridges too when they get lateral loads from floods, for example. And this one here, you can see another lateral road takes it away. Because of these sorts of bad actors that aren't fixed, these sorts of problems can happen. This is a Cherryville Bridge, and I'll play this. This is just a few years ago. Now there's a bridge so intact that is floating like Noah's Ark down a river. 2 hours it spent in the river and 186 feet long going.
The Cherryville Covered Bridge, built in 1927, carried away by the floodwaters of the Canaan River.
Well, that's sad. That's sad. That's sad. Been around here for 80 years. She's gone all in an instant. Nothing you can do. Just watch her go by. She'll find her resting place. Somewhere.
Never, never, never. I've never seen this before in my life.
It's a sad day for our community. Very sad. Because as we know, as every one of these covered bridges leave, there's never a covered bridge to replace it.
A piece of history lost, but also a loss with immediate consequences. The people who are now cut off.
There's 4 before you make the turn.
Jack and Diane.
Hazel. We have some elderly people over there, and we're worried about access. Our only access will be from on Havelock Road coming in, and that's a dirt road in through there. And obviously, with all the rain and everything's made it pretty severe on that road too.
It's something we played in all of our lives. And there'll never be another one like it.
2 hours later, as the sun sets, the old bridge gets caught under a new bridge, caught and held in place against the abutment by the fast-moving current. Catherine Harrop, CBC News, Coles Island.
And the story to tell here is the fact that that bridge was so solid and so intact, and it was taken away by floodwaters because they had no proper inspection techniques to find a few bad actors that were the primary cause for it failing in the lateral load, because at the reaction points at the seats, there was decay and they didn't find it. But the bridge was so intact that the contractor that got the job to take this bridge out of the river sold the wood in it to make 6 chalets on the coast near St. John. And so the story is what happens. We lose these valuable assets because we're really not able to find the bad actors and extend their life. If you look at the cost today of building new bridges, look how timber compares with concrete, culvert, and look how timber restoration compares with the other cost of new. Sequestering carbon, lower cost of restoration and life extension, and preserving the heritage are all the reasons. This is a huge Howe Truss under deck railway bridge in the CNR line out by Dawson Creek that we restored from a 25,000-pound axle load capacity to 80, keeping the bridge in service and restoring it by using high strength fiber, as you can see here, as the men get together high strength fiber that's Kevlar, full length of the bridge, and we lift it in with 30 men at one time and put this high strength fiber in place on the bottom of the tension cord and restore the strength of this bridge and keep it going. All part of the system we use to extend life. This is the longest railway trestle bridge in North America. It's in the CNR line. It's the Rochford Bridge in near Edmonton, just south of Edmonton. And you can see this huge trestle bridge made out of timber. They still run trains on it every day. And part of restoring this is using non-destructive testing technology and isolated bulleted fixes to keep things going. So bridges built with timber can last if built and inspected and maintained properly. Bridges don't have a use by date. This one in Golden, BC was huge glulam dug for I-beams, and the engineer said they're 42 years old. It's time for them to go. They came to me and said, well, it's huge build, Dan. What do you have to say? And I said, well, why is it time to go? So why is it time to go? Well, because they're a little old and they're gray and weathered and got some cracks on them. Well, gee whiz, guess what? If that's what determines the value of us, take a look at me. I'm old, gray, and weathered. Is my value gone because I'm old, gray, and weathered? No. And why would it be gone for a timber bridge? It shouldn't be. They asked us to come in and look at the Keystone Wise interchange down by Mount Rushmore. And this is a very famous interchange. And they were going to put 23 million into replacing them. They're nearly 50 years old, glulam beam arches and curved bridges made in Oregon and shipped into Mount Rushmore area. We inspected, found the bad actors, only 2 or 3 bad actors. The concrete deck had been replaced 3 times. The wood was there for the whole 50 years. And we designed a fix for them. It just went out to tender. And the total price of the tender is $4.1 million instead of $23 million to replace them. Why would we replace it? It's a beautiful, iconic bridge. And, you know, there's major floodplain and heritage considerations. We like to preserve the look, the environmentally friendly solutions. We want to, you know, look after public risk, I'm sure, but we can understand public risk and extend life. Look at these stats. Timber bridges are 22 times less energy than steel to put on for a unit load rating, 16 times less than concrete. And we remove CO2 from the atmosphere because we're using forest wood products, and we sequester carbon. The biggest sequestered block of carbon in the world today is in the stick-built homes in North America because we build our homes out of timber. So governments are struggling to deal with an aging inventory of timber bridges. The average age of a timber bridge in Canada is 82 years, many of them over 100. Maintenance costs, reduced ratings and so on are driving them crazy. And, you know, they get this poor choices for maintenance and it's cutting the life of decks. They're superstructures and substructures. Why don't we prepare and do the proper timber bridge inspections and the proper restorations? We have to find these bad actors that are on the bank. They're easy. The bad actors that are on the bank are easy to find, like these guys. You can see those. You know, my daughter can find these, right? And she's in biology. So, you know, it's easy to find those. These are the ones that are harder to find, that are just under the surface. These guys, the cavities in the middle, like this guy had a cavity in the middle of this bridge near Melbourne, Australia, and they'd missed it. And here's one of our technicians' heads up in the hole of it here, where we had found it with a non-destructive testing method called through compression wave, where we found this big cavity. And why? Because it had a vertical fastener that it started from the top, lets the water into the middle and it decays. So we look around and there's the cavity. That's what it looked like. And they had missed it. You can find it with non-destructive testing. Advanced inspection systems like compression through wave testing. You can see this is EFOD, electronic pulse highlight and outline diagnostic. And you can shoot a signal through the wood and it'll help you track where the decay is, how much is there, and how big the cavities are, as you can see here with Stephen. And we back it up with assay samples where we take cores and test these cores for species, grade, and so on. And these are, published domain situations where we've got proof from public domain about the relationship between loss of specific gravity and time of flight, so that we can find cavities like this without drilling all over the place and sound boring it and destroying the piece. This is an example of one here that failed. And why? Because they drilled the sound bore hole here and found the annulus to be 3 inches or 4 inches thick when it actually was this thin. And this is what resulted. The first pass over the bridge with a new triple T concrete deck, and they had a mobile home. It brought it to failure. I thought they were trying to copy my covered bridges by taking a hole out of this end and that end and having a new covered bridge. But that isn't the way forward. This is the right covered bridge. You can see here, Milky's Inlet number 1. It was designed for 12, and it was rated for 15, and it had a lot of heavies go over it. It was a beautiful, iconic bridge, and they came to that's what I just sent you folks today. This is just published out here today in Atlantic Forestry talking about this bridge restoration. I'm going to tell you the story about it now at the end of this session. We inspected it with rope access people, used through compression wave to find the bad actors. Everywhere in the bridge, we found the bad actors. We designed a restoration using the old drawings that were back from the turn of the century, helping ourselves to understand what it was that the designers meant to do. They wanted a camber in the bridge of 88 millimeters. They wanted a post dead load application camber of probably 25 or 30 millimeters. And we intended ourselves to be able to fix that bridge and restore camber. This is what had happened after they put a hog jaw underneath it. And that was the deflection in the bridge when we started to work on it. It was sagging 2.75 inches and resting on the hog jaw. This is what we put back into the bridge for camber after we'd restored it, by getting in behind these bad actor places where these heel plates had rust and decay and drilling a hole in there to find out what was in there, and figuring out the core by taking the core out of that hole and testing the core and checking the type of species that was in that core. You can see the core here, and this is a species identification where we determined that it was interior Douglas fir, this particular species, not coastal. Then we developed a whole schematic of the yellows and greens and reds of every element in the bridge, talking about what its rating was, what it was capable of. And that included elements like the bents and elements like the webs. And then we looked at places where that somebody had tried to put fixes on it incorrectly, and it almost ruined the bridge by putting these funky fixes on it that were not helping, they were hurting. And you can see the hog jaw here going underneath it. And look at this place. This was a king hanger rod where decay had cut in here. And the old cast iron had basically bent and pulled up into the tension cord, and the bridge was sagging around it, that big sag that was in the bridge. And you can see there was white rot, oddly enough, white rot. That's rot that's decay that eats the lignin and leaves the cellulose. And the cross braces had white rot, not brown rot on them, which was an interesting find. And we had witnessed overloading of the bridge between hanger rods, and that had led to bending loads at these stitching bolts here, because these are tension shear splices here. And you can see these nodes were all timber. And the laterals here, this is looking down from a hanger rod into how the webs had failed. So we had, look at this, exposed corrosion loss of this lateral tension strut. The wood was still intact and the steel or cast iron was gone. And the wood here was failed and we had to fix it. So we schematically drew all the elements that were bad in this 2-span bridge and showed how we were going to have to fix these individual elements. And so we set out to change this. The government wanted 30 tons. It was rated at 5. And we designed a solution to restore camber and bring the load rating to 30. And this shows you one of our drawing sets for it, where we developed this restoration. And it shows we redrew the whole 2-span and what we're going to do. And this was the old nail laminated deck that was on it that was done that we would have to pull up. And so what we did was they built a brand new deck with floor beams in the plant. These are each span of the bridge, and these are the new floor beams. And these is the new deck. It's a longitudinal vertically laminated glulam deck. And then we built big glulam beams with high strength fiber. and they were light enough that we could roll them out on tracks onto the bridge. And then we put rods down through the deck and used blocks underneath the deck. And literally each of these rod points allowed us to turn these nuts and use these lift beams which were supported at the abutments. They're 35 meters long, clear span. And we lifted the whole bridge back up with an 80-millimeter camber by carrying the whole dead load of the bridge. You can see it here before it goes in. And this is a picture of it here. And this is in the bridge where these vertical rods are down through the deck, and they're raising up the deck, and they're raising up the floor beams, and in turn raising up the truss and going for the camber we wanted. You can see them here. This is a fixed end moment connection that joined two beams, because their beams are way too long to ship. They're 35 meters, so we shipped them in lengths. And underneath we had these blocks, raised it up, and when we raised it up, that allowed us to restore using high strength fiber. And the high strength fiber was one continuous piece, full length, and this little piece of fiber right here is 5 times the strength of steel. And this fiber can be put on the underneath here and used to provide a continuum for strength. And this is Matt turning the nuts, raising the bridge up. If you can imagine, this bridge weighed 100 metric tons. And we have 2 wooden beams with high strength fiber that they're using to raise the 100 tons up. And through the placement of all these rods, they're restoring the smooth camber. And he's doing it by hand. And that allows this thing to be then retrofitted underneath, because these are the blocks pulling up the floor beams, and the floor beams are attached to the tension cord right here, and we pull it all up. You can see here, there's the block, the steel plates that were used to raise up the tension cord, and we put the tension cords by it, the new ones. And when we got it fully raised up, we had to take the old hog jaws off, and that was no small task. You can see the length of the cheater bar here. We had to oil and use penetrating lube on these nuts because they'd been there for 50 years, and try to undo these nuts because no one wanted to be the first guy to cut through that hog jaw when it was fully loaded. And you can see the nuts here as we got them off, and basically took that hog jaw away so that we could restore it with this fiber. The fiber then is wrapped in a roll and shipped on site, and then many men put this fiber on at one time. You can see them here putting it on using the cover plate. And one of the things that was extremely interesting about this bridge is, I live here in Jacksonville. I grew up here. You look all of North America, and where's the most extreme area for exposed and embedded corrosion in all of the country? Here we go, right in the Maritimes. And this bridge is right here in a severe exposed corrosion zone. So guess what's best to use when you're building bridges in these zones? Guess what? Timber. And so this is what happens to your steel and cast iron. This was the original width or diameter of the hanging rods. Look at this. That's embedded corrosion. Cold air gets at it and really reduces section in these key elements. Look at these guys here, the stitching bolts for stitching the tension splice blocks into place. You can see them here, stitching bolts. Look at this guy, 5/8 of an inch down to this in the middle. Look, embedded corrosion, worse than exposed. Look at these guys. All pieces out of the bridge replaced with galvanized pieces like this. Look at these guys, completely gone. Look at these guys. The worst parts of this timber bridge were the old cast iron and steel elements used to make it. And so that's what I have to say when it comes about timber bridges. Timber outlasts steel when it's properly designed, maintained, and looked after, as you can see here. These are the new hanger rods. We put them in galvanized special steel, and we put couplers up where we could get at them so we could properly tension them over time without having to have scaffolding built below. You can see the retrocom for compression reinforcement, putting on the top and all the elements, strategically reinforcing the bridge where it needed, replacing the old bearing blocks. This bridge didn't even have a connection between the truss and the seat, if you could imagine. It rested on the seat without any hold down of the bridge. And every wind analysis method we used showed the bridge falling over in wind, yet it had not. But if you designed by code, it was going to fall over. So we had to use proper hold down and remove these decayed blocks, as you can see here. completely decayed, and pieces of corroded and pitted concrete sheet. So we had to fix those with structural epoxy, as you can see here. Fixing the bridge in all these different areas, getting it back in service with a camera. It shows you a piece of wood where the rusted and corroded hanger rod had led to decay inside the wood in this area. And so we had to fix this area. We took the hanger rods out, put in new ones, but we had to also fix these areas where they were bad. You can see here. And both tension cords plies were bad at one spot. So we had to perform this kind of surgery on it by putting in engineered wood that was cut beveled properly with the proper holes. And we had some skilled craftsmen, you can see here. We lifted the bridge all up and we put in these pieces of trapezoidal Dutchman's patches, they're called. You can see them here, properly glued into place, and restored this great big bridge and these great big tension cords with these pieces strategically placed and strategically inserted for restoration of this whole bridge, to bring it back to service for 30 tons, not 5, and to provide for another 100 years of life. And wood in this bridge, we dated the wood, was growing in New Brunswick in 1695. And this bridge built in 1920, now 2020, is set up and restored, ready for another 100 years. That's a story in itself, talking about how this bridge can be restored. We restored the siding, we moved the lift beams off of it. We had finished the upgrades. We replaced the floor here, you can see, put in a new treated floor that'll go the distance with new floor beams to carry the load. They were properly connected to the tension. We put in strain gauges on the bridge. These strain gauges were placed in strategic positions. They're wireless, they're connected to a hub, and I can go on my phone right now and tell you what traffic is going across the bridge and if they're exceeding the design load limits. It's all being fed into our computers for monitoring. And you can see this is the first proof load test. We put a 27.4 ton vehicle on the bridge. It had a 7-ton hanging scaffolding on it. And we tested the deflection and we tested the dynamic forces, and we compared that in our strain gauges. And now our strain gauges are always compared to a actual 34-ton load on the 30-ton load rated bridge. And when we get the data, we can compare the strain that's going on every day. And every strain that approaches the maximum triggers a trail cam, and a camera comes on and takes a video of the vehicle going across the bridge that's overloaded. And this is a picture here of the chip seal that's on the bridge that's put on with epoxy. So the resurgence of timber structures, as I bring this to a close, is coming because of a wide variety of reasons. Environmental benefits, longevity and load rating, heritage, carbon trading, cost benefits, speed of construction. To fix the old bridges quicker and build a new one. Flexibility of labor organization, utilization. It's lightweight. It's the large dimension timber's got better fire resistance ratings, and the aesthetics. Timber bridges bridges built with timber can last longer if designed, built, and inspected and maintained properly. In closing, this shows you another bridge in New Brunswick. It's called Vaughan Creek. It's an old bridge too. And the government said, we're going to take it out. And they didn't want it. And they put in a Bailey Bridge beside it when they improperly designed solutions to fix it. And that's the one right there. And the people got up in arms so bad when they heard they were going to take the bridge out that they protested and got in front of the bridge. And I made a presentation to the Premier. Blaine Higgs is a friend of mine. He's the Premier of New Brunswick. And I made a presentation to him and the minister and their senior engineers and tried to convince them that a new covered bridge would be the way forward if the old one was gone, and to have a carbon-friendly solution. And I'm pleased to announce that contrary to what they were going to do, which was put out a fake covered bridge on a precast concrete girder system, they put the tender docs out just a few weeks back and said, we want you to build a full timber covered bridge. And this note in here you can't read says, ignore the concrete, we want timber. And so in closing, I just want to say that thanks for taking the time to listen to me. And, timber bridges and the restoration thereof is the way forward today. Thanks.
Brilliant. Thanks so much, Dan. That was excellent. Gosh, you whipped the solutions and the investigations were countless. I think I know for one, I'm going to be going back through this presentation with a pen and notebook. There's so much to learn. Thank you so much. I'm going to kick off with questions. The fascinating solution, the high strength fiber reinforcement to the soffits of the beams. And you mentioned fixing with plates. So what is how were these fiber straps fixed?
I understand you. Yeah, good point. So the strategy is, hey guys, is to you got a lightweight system that you can roll on the bridge, grab the bridge and lift it in the air to restore the camber, so it's a total load fix. So you get that. So just like I would be total load fixing a building, a queen hammer truss or something like that, I pull it back in the air because it's been sagging. I pull it back in the air, I restore it, and then when I let the sag go, it's like new again. Well, so we lifted it up, got rid of the sag, and when we had it held by the two big girders, then we could do all kinds of stuff. And so we fixed bad elements, did this, did that, did this, did that. And then the last thing we did was on the bottom face, the soffit, as you so properly called it. That was a good choice of words, Doug. On the soffit, we put the high strength fiber. In the fiber, the fibers are pre-tensioned. When you make that fiber, they stretch the little filaments of fiber and then they cure an epoxy around them, a polymer. And then it comes on a roll. And when you unroll it and put it on the bottom soffit, it glues to the bottom of the soffit so plane sections remain plane. And you use leg screws to squeeze the glue and thin up the glue line, because pressure doesn't cure glue. What you want to do to cure glue is thin the glue line to 0.004 of an inch or less, because it's thin glue lines that make for the bond. So we leg it to the bottom and close the glue line. It cures in place. And then, of course, once it's post-cured, you're good to go.
Excellent. Great. Now, anybody else? I mean, there's lots of thank you and excellent presentations. Excellent. There's somebody who's saying, Maria is saying it's a very important point to decide to restore a wooden bridge, preserving also the cultural landscape that is part of the site history. Everybody's saying excellent and inspiring. Well done, Dan. So the other thing that, just to make clear, on the one bridge that you explained their conservation and repair process, the laminated support that were rolled into the bridge. So those were just temporary works.
Yes, right. Yes.
Lift the bridge and restore the camber.
Yeah, and what we did is we fooled the bridge, Doug. What we did was we made these big beams and we made an assembly. You could see it there in the aerial photos. And we put tracks on the bridge, MC channel turned open face. Yep. And then all we had to do was put a little cable and pull it in. We towed it in on the tracks. You didn't have to get on it. Well, we adjusted the dollies that were under the front of the beam going onto the bridge and brought the rear dollies way in, so that the cantilever across the rear dollies on the back end of the assembly caused the front end to be lifted up. And that allowed us to keep under 5 tons, you see, and get that front dolly across the bridge without going over the old load limit.
Right.
Once we got it across, then we jacked up the ends of the beams, put blocking under them, and put that load right back down on the piers, so that the piers were carrying the load of the girder ends.
Right.
And then we dropped the rods from the top of the girder with saddles down through the floor beams and saddled underneath the floor beams and used the bridge own system to lift up. And when we had the threaded rods, they had nuts on them. And the guys I did it actually, because I was really keen on it. And some of the cheater on the wrench was only that long, 1.5 feet. But because we had so many of them and we had the torque advantage, we lifted 100 tons with men turning the rods that were 1.5 feet long, with wrenches 1.5 feet long.
Right.
That's what made it really unique. It took about 2 hours to lift the bridge.
Gosh.
By 10, but 2 hours, because we had to lift it carefully. You couldn't lift one spot 7 inches, right? Because you'd break it. So you had to lift it in a camber to recreate what it was when it first was built 100 years ago.
So that's what I wanted. So the temporary beams, were they designed with cambers, or did you insert the beams and then form a camber and then lift the beam?
No, the beams themselves, those girders had 12 inches of camber.
Okay.
12 inches. So I set a limit as an engineer of L/120. I said, you can't, the length divided by 120, that's the maximum deflection. And so we deflected those beams 12 inches to raise the bridge up 8.
Right. Okay.
Yeah.
Couple more questions. There's a few coming in. Maria Elena is saying, is the your high strength fiber, is it always carbon fiber? And what is the adhesive you're using?
I understand you. Well, you noticed I had all those patents. Part of what I developed over the last 40 years in my life was how do you make this RP, we call it RP, reinforced polymer. And the reinforced polymer can be made with Kevlar. The generic name is aramid. And Kevlar is made in Northern Ireland or Holland. And that's the fiber. Or we can use carbon fiber, or we can use glass fiber. And that fiber comes on spools, bobbins. I showed it in the picture there. And we pull them through a pultrusion device and form up the epoxy around them, making a strap out of it, a strap. And that piece is made in such a way so that when you prepare the surface, there's little fibers stick out of the surface. And we use a 2-part epoxy that cures quickly. You have to have the RP on that full length of bridge. You saw the 30 men doing the Howe truss.
Yep.
They have 55 minutes to get it on. 55 minutes. And the epoxy needs to be applied and the surface closed in 55 minutes. The close time is 20 minutes. That's the time you start turning the legs. And the cure time for 92% of capacity in the glue line, the cure time is about 4 to 6 hours. So when you reinforce that bridge, if you had it done last, you could have rolled the assembly off and put trucks on it a day after you'd done it.
Good grief. That's amazing. That's brilliant.
Yeah, thanks.
Now,
that's it.
Another question, and Maria, hope I'm getting this right. Maria has noticed that there's in the shape of many of the covered bridges that the shape appears to be hexagonal. And she's wondering if that hexagonal shape has to do with the strength, the structural design of the bridge, or is it just aesthetic?
I understand you. Traditionally, not always, but I would say at least 70 to 80% of the through truss, that's what they're called, through truss bridges in Canada are Howe trusses.
Yep.
That's the predominant type of truss. And what these truss designers realized hundreds of years ago was that if they separated the tension cord from the compression cord by a big distance, they could carry heavier loads a longer distance. And the whole idea is the mechanical leverage advantage. Have the tension cord here and the compression cord here a long ways away from it, and that gives you a lot of leverage to resist load. So these through trusses are generally square. They're rectangular. They're this way and this way. And what you do when you build the covered bridge is you've got to have the gable roof, the side walls, and inside the bridge to hold the roof is a bent. And the bent is a square bent, and in that bent are fillet braces, knee braces. Yeah. So what they do to keep trucks away from the knee braces is they put A-frames on the start of the bridge to keep trucks under height. They put lines on the bridge surface, and they put that shape you see on the entrance to keep the truck from getting left or right and getting into the knee
Yes.
braces. That's what that's about. So
We-
typically the shape is about the facade or the covering.
Right. We've got a lot of iron and steel bridges in the
Yes.
counties around
Yes.
where I am, and they're slowly
Yes.
getting rid of them. But you could,
Yes.
there are many of them are Pratt and Howe trusses.
Yes.
But of course, in a Pratt truss through truss bridge, you've got the portal frames at each end,
Yes.
and they take one hell of a knock.
Yes.
They're all bent
Right.
and battered, and
It's
yeah,
true.
they do. But the portal frames at the fronts
Mm.
of the trusses
I
take a lot of beating.
just designed, our team designed 2 bridges in your area, Doug. Walkerton and up toward
yes.
Aurelia. And they're replacing old pony truss, steel pony truss built in the 20s. And we're going back in with new timber bridges.
Well, we've got 2 pony truss bridges in the county that are the oldest of their type in North America.
Wow.
So I'm going to be campaigning to keep them because I know the county is trying to get rid of them. I'm going to be campaigning to keep them. We've got about half a dozen bridges, steel bridges, that are the kind of the rarest and oldest of their type in North America.
Interesting. So, wow.
Yeah.
Wow.
Somebody else just got a, where does Phoebe's question go? Phoebe's question: has the fiber reinforced polymers been used in any other historic structures?
Absolutely. I don't know if you folks know about the Frank Lloyd Wright building in Racine, Wisconsin, called Wing Spread. I restored that that building totally. We built a building over top of it. I've got a lot of Frank Lloyd Wright buildings, great architect, not really good engineer. And so a lot of them were decayed. And so we were commissioned to build a building over the Wing Spread building. We removed the roof from the top because the Heritage Foundation wouldn't let us remove one piece of crown molding or base molding, nothing. And so we stripped the roof back and used what we call zebra beams made out of carbon and southern yellow pine veneers to replace all of the struts. If you're familiar with Wing Spread building, that's one I restored. Many other buildings, big buildings that I've restored over the years, big, tall, long span buildings in Fort St. John's. I have quite a few buildings up in Europe for the Europeans on the line. In Krakow, where the old Pope was born, in Krakow, Poland, the big, huge farmers market in Krakow, Poland is mine. That's my design. Or if you're in Vienna, the Blaha building, the Blaha, B-L-A-H-A. And can you imagine this, in the water treatment facility there in Vienna? Those are my buildings. And I have them in Germany and Northern Italy and in France. A lot of different buildings, either built in timber or restored with high strength fiber. That's what the question was, I think.
Okay.
My last continent to work on is Africa, and 1,350 under seal. And I'm hoping to get into this year to South Africa, to Cape Town, to restore a bridge built during the Boer War.
When you do, can you come back to us and give us another talk? Because we're keen on extending sort of the wood committee into Africa. So whoever you meet, get to know them, tell them about us, and then do a presentation for us as well.
Well, Paul Matthews was in one of the pictures. He's an engineer, an avid fan of wood, and he's from South Africa. His family's there. He was in one of the pictures. He'd be glad to. Someone asked if I had worked on covered bridges in Oregon. The answer is yes. From Corvallis, a covered bridge there in Oregon, where Oregon State University is. And they've asked what the cover of the bridge's function is. Pure and simple. The cover's got one purpose. It serves one purpose, and that's to keep water off the joints. So if you're ever wondering why is a covered bridge covered, that's why it's covered. It serves a purpose to keep water away from the connections.
Well, this reminds me of Charlie Brentnell's talk a month or two ago on the Kinsel Trestle in Vancouver Island,
Yes,
and that he repaired with Gord MacDonald.
yes, know them
And
both.
the one big comment to the takeaway from that is with the majority of the decay was in the angle between the various timber elements,
Yes,
and that's where the majority of the decay was.
yeah,
So if
our
you can
senior,
cover those,
that's it right there. Our senior engineer, Reed Costley, he's our Canadian engineering manager. He was the designer on that. He worked for ISL at the time.
right?
Yeah, it's quite a job. Just down the river from down the track from that, there's another huge, tall timber bridge. There's a lot in that line that got to be fixed, that the government's got the charge to do. And I'm glad they're getting the energy and inertia to fix these old timber bridges. They're part of our heritage. They're our culture.
Excellent.
Mm.
I think, what are we coming to? We're just 10 past. So,
I had a quick question, Doug.
oh, there you go, Joe.
So, yeah, it was about the coastal Douglas fir and the inland Douglas fir, Dan. I
Yes.
wondered how you could tell the difference under the microscope.
Interesting. So in coastal Doug fir, basically what we have are non-aspirated pits. So if you think of the pits as a lifesaver with a diaphragm in the middle, what we look for to identify the difference between inland and coastal is whether the pits are aspirated. If they're not aspirated, that means they're still open. Treatments will flow more easily through the depth of the wood. Flow of moisture in wood is 100 times faster parallel to grain than side grain. And so when you treat wood, you got to try and get the treatment into the wood. And people think with incising that what that's doing is injecting the treatment in the wood. It's not. All incising does is open up end grain to increase uptake. And so when you're looking at these old bridges that are treated, either with a lumen treatment like creosote or a cell wall treatment like, say, pentachlorophenol or copper naphthenate, what you look for is the way the chemical has got through the sidewalls. And coastal Doug fir is not aspirated in its pits, and it lets travel happen much better. So in bridges, one of the first things we look for is whether the Doug fir was inland or coastal. The same thing goes with spotty, what we call spotted gum. There's 672 hybrids of eucalyptus in Australia, and they hybridize. And when they hybridize, certain types of eucalyptus will lose its tyloses. And tyloses is a viscoelastic bubble that grows in the lumen of a cell that makes it hard for the hyphae of the fungus to get through them. And if I'd have gone on faster, I'd have showed you more in my presentation because I have a whole bit about it. And someday maybe we'll come back and I'll show you that whole bit about how
you can come back and do another one.
Yeah, right. So anyway, this hyphae grows through either the interstitial spaces, the lignin, and the hyphae has a foot on the end of it that secretes an enzyme, and the enzyme is acidic, and it either breaks the lignin down first, which is called white rot, it leaves the cell, or breaks the cell wall down first and leaves the lignin, which is brown, called brown rot. And there's about 6,800 types of each in the world today. And of course, decay is critical in timber structures, as you know. And there are 3 ways we prevent decay. Well, look, all we need to know about wood really is if you can keep the water away from it so that it doesn't have moisture content over 22 to 24%, it's not going to decay. I mean, in King Tut's, where he was buried inside the tombs, guess what? All the wood artifacts are still intact. And why are they still intact 3,000 years later? Because there's no moisture.
Yeah.
Or if you get logs down in the bayous in Louisiana that they're bringing up from the mud, why are the logs still intact for sawing up for flooring? Because there was no oxygen. And if you were skidooing across the northern tundra of Manitoba, and like one guy come across a stick coming out of the snow, and you dug around the stick and found there was something down there, he comes back with imaging, and he images out, and they dig down and find the Investigator, HMS Investigator, locked in the ice for 160 years, and is still as good as the day it got locked in the ice. the skeletons are laying in the beds underneath the blankets. Everything's intact. Why? Because the wood was in the freezer. It was below 5 degrees Celsius. Wood won't decay below 5 Celsius. Why? Because the hyphae contains a liquid to carry the enzyme. And when it's too cold, the liquid doesn't move in the hyphae. So if we understand these things about how wood decays, it'll help us understand how to fix it, how to keep it going. And the old designers knew from England and Europe, they knew something. If I put a cover over an old howe truss in the most highest embedded and exposed corrosion zone in all of North America, I can have covered bridges that last 100 years or 120 years. It's a knowledge is power, isn't it, guys? Knowledge is power. And so when we know what to do, we can know what to fix and how to fix it. And that's what it's about for restoring wood.
No, brilliant. Brilliant.
Yeah.
Thank you. And,
Yeah,
and
no
showing
problem.
that bolt that had caused that big cavity, that
Yes.
was very instructive.
Yeah,
Yes.
it's the verticals from the top that kill you in bridges. And
Did
I
you
know
try and design them out?
I take them out. I have engineers, a bunch of them that work for me, and they all know one sure way to get fired. And that's to put a design in front of Dan that has a vertical that comes from the top. That's the sure way to get booted from our company. Because, you know, I'm not going to be party to something that shortens the life of timber.
Yeah.
Why would I do that? That's crazy. I'm a
You've
boat
learned
timber.
from the past.
That's right. Learn, and I'm not particularly smart guy. Mom used to say, Dan, you're not that particularly smart, but you're damn persistent. That's what Mom used to tell us as kids growing up. And so I'm not that smart. But when you've had enough time, 4.5 decades, to see something you did wrong, 4.5 decades not work out, that's where it comes from. James Taylor and Carly Simons had me design the first bridge I ever designed to see the total eclipse of the sun in Nova Scotia. Who's listened to the song? Total eclipse of the sun.
Oops.
Yeah, it tells your date.
Yeah.
And so I had my first bridge. I'd get out of college as a young engineer, and they wanted to get connected from the mainland of Nova Scotia to an island. They said, Dan, when you design me a bridge. So I'm an engineer. I never had any bridge training. I went to UNB, took forestry and engineering, civil engineering. So I get out, what did I do? I looked through the BC Forestry Bridge Manual, and I picked out all my ideas from it to design this bridge. Well, those ideas were 100 years old, and they had all kinds of vertical fasteners from the top, and I did it wrong. And I often say to people, look, 100 years ago, people died from appendicitis, right? Do people die from appendicitis today? Why would we do the same things today that screwed over bridges 100 years ago? Why we do them today? Learn from our mistakes, do it right. And the one thing that those designers and the covered bridges got right, which is why it was the focus of my talk today, what did they know? If they put a cover over their howe truss, it would last a dime.
Good.
Yeah, that's it.
Speaking of which, Kathy McDonald wants to know whether the new St. Martin's Bridge has been finished yet.
New went out tender the 1st of May. They have not awarded that tender yet to anybody for the deal. But as soon as it gets out, I'll be keeping the committee up on it because it'll be beautiful in timber.
Brilliant. Good. Look forward to that.
Yeah. First one in 5 decades built in timber in New Brunswick.
Well done. Well done. Okay. Does it, just to let everybody know, Insook and Manvi have shared a few photographs of bridge in covered bridge in Kashmir and one in Korea, which you can all have a look at. Thanks for that, guys. Oh, and here's another one from Insook. Good. I'll tell you what, if in case anybody didn't get them, I'll download them as well.
Perfect. Thanks.
And I don't see any more. Oops, I don't see any more questions coming in.
I have one, Doug.
Oh, there she is. Hi, Manvi.
Hi, Doug. Hi, everybody. Thank you, Dan. This was amazing. Totally loved the floating bridge story.
Great.
I had one question, actually two. The first one being that you saw white rot on the cross beams beneath the bridge, and on the other
Yes.
side, right next to it, there was brown rot. Is
Yes.
there an explanation for it?
Yeah, it was really a great question. Great question, because I really enjoyed getting down underneath there and finding that white rot. It was fibrous, you know, you could peel it off with your fingers. It was the hemicellulose and the cellulose remaining when the lignin was gone, you know.
Right.
And I was really keen on it because it was one of the few times that I was actually able to show students white rot close to brown rot, if you know what I mean. And so we started to take it in the lab. We look, why were we witnessing white rot and not brown rot in this particular case? Well, what we found is that white rot tended to grow more quickly in cases where all the moisture was being carried through the air. And so the fog that was coming in with the tide every day, twice a day, the fog would come in, the heavy fog would come in over the water, and it would tend to take the surface of the wood and saturate the surface with the fog. Are you following me?
Right.
And we found out from that the fog had a little bit of salt because it was coming from the ocean. And this little bit of salt from the fog tended to shut off the brown rot more than the white. And that was an interesting thing for us to find out, because where the cross braces ended up on the tension cords, that's where the moisture came from different places, and that's where the brown rot was. In the cross braces, the moisture was coming from the fog in the air twice a day, and that's where the white rot was. So we have a paper that we're in the process of developing because it's an interesting find. I don't think it's been published before. That's a great question.
And picking up on that, Susanna was wondering if they were on the same species of timber.
I understand you. If for the most part, there was a mix of species. There
Okay.
was spruce, there was some balsam fir, there was white pine, there was Douglas fir. As you can imagine, 100-year-old bridge, there was a kind of a potpourri of different types of wood that were left in it from changeouts. You know what I mean? So that didn't tend to be specific. In other words, it wasn't just Doug fir, for example. It was in the cross braces. There could have been other types of species in there.
Right. Okay.
Yeah, interesting. Good question.
Alan here.
Anybody else?
Question?
Alan.
Yeah. Just out of interest, what's your ability to find suitable trades? Because I mean, this isn't pouring concrete. You have to be a much more inventive,
yes,
and different trade than normal. I mean, by default. I mean, I know
Yeah.
that I do this every day. I just wondered how you find that, how that works on the tendering process, and all the problems that go with that.
I understand you, Alan. And so often, isn't it the truth that it's cheapest price, eh?
Sure.
The government doesn't understand anything but money, you know, and so they're looking for cheapest price. What we do is I teach 16 different courses. Our teams teach these courses. And all of the people that worked on that Milky's covered bridge, which, by the way, Milky's is a Maliseet name for drying or whatever. And the Indians used to dry the Gaspereau and hake that they would catch out of the river coming in when they come in to spawn. They dry them there. That's where the term Milky's comes from. It's a Maliseet name, but it's Bayswater Bridge, but the term for it is Milky's Inlet. And the men that we worked on that bridge with, there were 10 of them, all had to take a level 1 and 2 course. And they had to go through the whole process of how do you apply high strength fibers and how do you work on it. And the guy that cut that trapezoidal piece, that did all of that craftsmanship work at Hangar 1, he was from Petty-Kodiak, a place close to Moncton, and he goes around the world with our team doing just that. He'll actually get involved with the team to go do it. So the idea that you're going to find covered bridge skilled technicians, that's not going to happen. So what I've tried to do is convince the government. They have 250 bridge maintenance technicians. And I think I have them convinced to take 6 of them and train them and call them specialists and move them around the province to fix their covered bridges.
So are you saying you would build into a tender price basically an amount for training?
Yeah, absolutely. Got to.
Excellent idea.
Yeah, you can't, if you go out in the street and find somebody with $5 and a hammer, because everybody that wants to be a contractor has got $5 in their pocket and a hammer, right? And
Yeah.
so what do they want? They want cash flow. And so
Yeah.
the first thing they want to do is underbid a job. And so they get the cash flow because they're starving to death. And so at the end of the day, what they're doing is they're taking these jobs and basically living off that cash flow. Well, if you let them at these precious covered bridges and these timber structures, you're going to end up coming out the other end with something worse than you started with. And when you look at these covered bridges, if you want to find the spots that are really degraded, it's usually something's been done to them.
Right.
Typically something's done to them. It was
Yeah.
not the bridge's fault. It was someone who mishandled and mismaintained it. And so I teach these maintenance and restoration course. And right now, the National Research of Canada has just retained me to write a new book over the next 12 months, all next winter. I'll be writing a book on conventional and advanced practices for timber bridge restoration and maintenance. And this will become a textbook, one of the first of its kind, for restoration and maintenance of timber structures that they'll use at the university level. And it'll contain detailing, showing how to design certain connectors and what details to use. Because what did I miss when I designed Carly Simons and James Taylor's bridge? I'm a young engineer. I don't know. No one's going to pump it in one ear and say blah, blah, blah. And nobody taught me. So I went looking through the literature for references on how to build a proper timber bridge. There was none. And so what we've convinced the National Research Council of Canada through Canadian Wood Council is to develop one and have a new textbook that we can have out for university students and other. How do you go about detailing the restoration of timber structures? Well, important.
That will be hugely beneficial to the whole field. We all look forward to that, Dan.
Thanks.
Anybody else with questions? Who's still out there? We still got. Yeah. Phoebe, did we answer your question? I'm not sure if I'm okay. Good. Good to see a few others. Tobias and Lisa from Sweden. Excellent. Do you have any covered bridges in Sweden?
Yeah, they do.
They do. Okay.
Oh, absolutely.
You worked on any there?
Yeah, we sent a whole team over to Scandinavia to look at timber bridges, and they lead the way in the world designing and building timber bridges. Scandinavia is a leader in the world in it.
Great.
They're a great example to follow in Canada. And there's another question that comes in about roof wind load.
Yes.
When you cover a bridge and put a big piece of wall up in front of the wind, you got a huge load that you have to consider. And wind loads are a big factor, and we're a big factor in this covered bridge at MIEAust, for example. I always tell my students when I'm teaching, I say, if you don't think wind's a big load, get somebody to take you down the road in the back of a half ton or a ute and try to lift up a piece of 4x8 plywood and hold it against the wind. Try to hold it at even 30 miles an hour. And you see where you're going to go. You're going to go off the back of the truck. And that's how I teach my students about wind and the fact that it's powerful. It moves ships back and forth across the Atlantic to carry goods for hundreds of years. If you don't think wind's powerful, just look at sailboats. And so when you're designing a covered bridge, you have to think about wind, man. And the funny thing about it was, remember me telling you, the MIEAust covered bridge had no hold down bolts in the concrete seats, none whatsoever. I mean, it was an amazing story. And in the wind, the locals would tell me when I got there, because I didn't know, in the wind, they said you could feel the whole bridge rock and it would lift up on one side. And they would all wonder what was going to go on. The bridge itself would rock off of its moorings like that.
Wow.
Crazy, I mean, really, what they got away with.
It must have been great for the kids. I can see,
yeah, right.
If I was a kid, it would kind of be a weekly thing. Oh, let's go down to the bridge and feel it.
Rock and roll.
And feel it lift. Yeah.
Right.
Must have been great fun.
Yeah.
Okay. That was a beautiful illustration of the power of wind. Yes. Excellent.
Alan, here, one more question, if you know.
Okay.
You mentioned the glulam arches somewhere down in the States in the circa date of 1950.
Yes.
Out of interest, what type of adhesive was that used? And do you know the rough date when they started bringing in epoxy for glulams?
I understand you. So the date of those beams was in the 52 through 56. They were penta-treated as laminates before they were glued. And the glue that was used was a phenolic glue, resorcinol. It was a waterproof glue, and it was put together using about 1 MPa pressure to squeeze them. And epoxy glues are used for quick cure, but not used to manufacture glulam beams. If you're buying today, you folks have all heard about mass timber, CLT, cross-laminated timber. It's made a lot of it with polyurethane glues, quick cure. They're foaming glues, and they quickly cure to, make the process of manufacturing fast. But they'll only penetrate the wood about 1/16 of an inch, whereas a phenolic glue on a cold cure penetrates the wood about 3/16 of an inch, and you get your moisture cycling resistance to delam. So in the epoxy, the reason we don't use epoxy in the manufacture of CLT and glulam and other engineered wood is that 2 reasons. One is it's 10 times more expensive than a water-based glue. A typical water-based glue like a phenolic cures by dehydrating. That means it's about 50% water. You put it on the surface and you use dry wood to glue. That's why it has to be dry, 12 to 15% typically. And what happens is the wood sucks the water up, dehydrates the glue, and it cures. That's how engineered wood cures. Epoxy glue is a chemical bond. The molecular weight is much larger. It doesn't penetrate the wood at all. It lays on the surface and cures 100% solids. And epoxy glues, because they don't penetrate, are chemically bonding things together. Well, what happens with epoxy glues is they have a lot of OH or hydroxyl groups. And when you get moisture with them, they soften. And so the automatic boil test and water type test don't tend to work very well for epoxy type glues. So when we're restoring things, we use a special 2-part epoxy that resists that moisture softening and heat softening and does the job. But traditional epoxies that are much cheaper just won't do it. To put it in perspective, the epoxy used on Milky's is $678 USD per mixed gallon.
That's a lot of money.
A lot of money.
Wow. Wow.
Well, it's special. It's not what you get at Home Depot or something, guys. It's, it's special. Yeah. Yeah.
Susanna has a question, and Susanna, forgive me if I am don't ask it properly, but asking if maybe you can see it there, Dan, as well, for replacement glue or replacing or repairing glulam members. Are pressure treated is pressure treated wood used, and with what preservative system?
I understand you. When we make a glulam beam, current code does not allow us to pre-treat the laminations like the Keystone Wise Bridge at Mount Rushmore. Today, codes won't let us pre-treat because the pre-treatment lays havoc with the cell pores and the cell lumens, preventing the travel of the moisture and of the glue. And so you can't do it. So we treat glulam beams post-manufacture. So we always machine glulam beams and then treat them, and typically with an oil-based treatment. Why? Because if you treat it with a water-based treatment like CCA or AZQ, water-based treatments tend to swell the wood. So if you're treating it with a water-based treatment post-machining, all your machining screws up. It gets distorted. So you only treat with an oil-based treatment post-machining, because then you don't screw up the machining. And you don't produce what's called bright wood. Bright wood is untreated wood. So when we're treating things today to protect them, preservatives are used. Typically oil-based preservatives are required by the bridge standard for outdoor stuff. People see brown and green wood used for decks. Well, I call that's marketing. Those types of treatments leach out of the cell wall, go back into the ground. And Obama coined the phrase, you can put lipstick on a pig, it's still a pig. The bottom line of the story is when you're using water-based treatments that flow out of wood with mobilization of water, it doesn't really give you longevity. The best is oil-based preservatives that fix against the cell wall and go the distance in terms of treatment. My favorite is pentachlorophenol. Copper naphthenate is another one. There's some other ones that are out there for preservatives. There's 3 ways to protect wood, guys, besides being smart and keeping the water away from it. The first one is preservatives, which make the wood inedible. When you put a preservative in wood, it goes up against the cell wall. And when the decay-causing hyphae grow around and their foot secretes an enzyme, the fungal colony can't eat the wood. It's inedible. The second is a fumigant. A fumigant uses very low vapor pressure to basically move through the wood, and it kills the decay-causing fungus. And as soon as the concentration drops off, the fungus continues to grow. And the third is called a diffuser. It's the most recent, and I like to use it the best. I've used my share of trichlorotriptyline, which is a fumigant, over the years, but I use diffusers now because they're salt rods. Basically, you can touch them and they're salt, and you put this salt rod in the wood, and when the moisture hits 22 to 23%, these salt rods are anhydride. That means they take the water out of them. And so when the moisture in the wood gets at about the point decay starts, it draws the salt into a brine, and it moves through the wood and neutralizes the pH wave caused by the acidic enzyme. And those are the 3 ways we treat wood. And if you've got an old timber structure today, I recommend the use of small diameter diffusers as a way of preserving wood in a non-toxic way.
Did that answer your question, Susanna? Are you still there?
Yes, it does. Yes, it does. So for diffusers, you would use boron rods typically, or
boron is a fumigant. What you might be thinking of is borates.
Borates, yes,
yeah, borate
rods.
rods like Cobra rod and some of the others. You have to be a little careful because they mix certain things with them, to get insecticides and other things. And so I don't use stuff that's mixed with them because I kind of want to be able to touch and feel it and not have to put a triangle up on the building. So I use salt. And it's funny, some of the old things, even though they are 100 years ago, are still good. And in addition to covered bridges, one of them is rock salt. In British Columbia, they sprinkle rock salt on all the timber decks out on the roads. And they do that not for the ice because the winter's gone. They put the salt out so that the spring rains will flush the salt into the wood and prevent it from decaying. So the salt acts as and people ask, well, why is the salt working? Is it the same way you put salt on a wound to try and kill diseases and so on? Well, no, that isn't how salt works at all. The salt is a base that neutralizes the acid of the enzyme. It's about neutralizing.
Okay. So for the preservative, would you go with light penta or would you go with creosote?
Oh yeah, somebody who knows their treatments. You bugger, you're sneaking in on me.
No, I don't.
You use terms there. You can't fool me. You use terms. There's 2 types of solvents with penta, light and heavy oil. You're talking about that.
Yeah.
And the light is generally like a mineral spirits. And the reason we use that light is because it's not sticky to the touch and evolves surface quicker. The heavy oil tends to carry the reactive agent, which is about 5% of the solution, carries it deeper and gets it more fixed to the wall. So timber bridges for railways and highways tend to use heavy oil solvents for that reason. It's about longevity.
Okay.
Typically what I'll do, because I'm not a tree hugger, but I am sensitive to environment, and I've become more so as I got older, is nothing beats fresh drinking water, is there? And so, what I do with my bridges is I put Alaskan yellow cedar on my handrails. I don't treat those. Alaskan cedar does the work, and it's a nice wood, and I stain it the color of the bridge. And it's just because I'm like that, right? But I want to keep the bridge underneath treated, so I put a heavy penta solvent or copper naphthenate. Yeah, copper naphthenate's another one, again with heavy oil.
Okay.
And for people that are trying to do this, another little tip to just share 45 years. save you a lot of money. If you're going to pave or asphalt over a deck surface that's been made with heavy oil, don't put a tack coat on it.
Okay.
Just another little tip for you. It'll save you a lot of money because the tack coat will blister the asphalt. Yeah.
Thank you.
Yeah. Thanks for the question, dear. It's nice of you. Yeah.
Maria, I think she didn't quite, if you could just say the name of the oil preservative that you were recommending, Dan, say it again.
Okay, so the oil solvent is the carrier of the reactive agent. So in other words, you could have pentachlorophenol as the reactive agent, or copper naphthenate, whatever. They are cell wall treatments, and the solvent is oil that carries them. And the heavy oil is really nothing more or less than number 2 diesel fuel. The mineral solvent, the mineral oil, is something more like tung oil, mineral spirits. It's lighter, less viscous. And people get confused because they think the less viscous will go deeper. That's not the way it shakes. The heavy oil is giving you the better penetration and the better uptake. And that's the solvent, and the reactive agent is giving you the preservation. It's about 5%.
How is that, Maria?
What about the river water and the pentachlorophenol or the creosote? What about river water?
I understand you. So in some parts of the world today, they specify creosote treated wood to be in rivers. That's what used to be the case for hundreds of years. It's an old coal tar. They heat up the coal tar. They put the wood in a vacuum pressure chamber. They draw a vacuum on it, pull the water out of the lumens, and then put the coal tar heated into the chamber and put pressure on it and put it into the space where the vacuum's created. And that's called creosote treatment of wood. Well, the problem with creosote is they couldn't get the air out of the centers of the piece. So when they pressured in the coal tar that was heated and then put the piece of pile or timber out in the river, what happened was the summer sun would hit the coal tar. It would make it less viscous, and the pressure inside the piece that was created from treatment would act as back pressure, and we get what's called expression. And it would express the coal tar out the sides of the pile, and you'd see dripping coal tar. Who's seen it before? I'm sure you have. And that's called expression. That's the term.
And that the same as bleeding? Sorry, Dan.
Yes, it is.
What do you call bleeding?
Yeah, it's bleeding. And so that coal tar expression is a technical term. It would drip down and get in the water. Well, downstream, guess what? The fish are turning upside down, right? Nobody likes that. You get a sheen on the water, the fish turn upside down. So I stopped about 10 years ago speccing creosote treated stuff in water. I just don't like it. And some places do. In New York now it's outlawed. California is outlawed. A lot of people are getting rid of it because it's just not fun. Now the business of having penta or copper naphthenate near a treated water. Now, I would rather have oil-based treatments like copper naphthenate or penta near or in fresh water. Why? Because it doesn't mobilize. If I put copper naphthenate, if I put CCA treated wood, the green stuff or brown, AZQ, any of the water-based treatments, if I put them in wood and I put the wood in water, guess what happens to the treatment? The minute that water gets in the wood, it remobilizes the treatment. And where does it go? Down the river. And if I had time, I'd be showing you precipitate, it's called, getting into the river from those. So I don't choose water-based treatments. If you go to the major bridge standards, they will all tell you not to use water-based. They say use oil-based just for that reason. So I don't like, a lot of engineers still design with lumen treatments, creosote for rivers. I don't. I go with fixed wall treatments, an oil-based product, so that I can pre-machine, post-treat, and not expose bright wood. And bright wood is the term to untreated wood. People often ask me, and they'll say, Dan, I'm going to Home Depot this weekend, and I'm going to buy some wood to make my deck out back. And so they'll buy wood from Home Depot. It's clean, it's fresh. And you'll hear them going, you know what they say? They say, I brought fresh wood from Home Depot. It's not decayed. I'm going to build my deck with it. Well, they don't realize that there's microscopic spores all over the place. They're on that wood. And the minute the environment reaches a point where the wood can be over 22% moisture, the temperature 5 to 35 C, and the temperature, moisture, and hold on here, it's coming to me. There's temperature, moisture, and
jump in, Susanna. Come on.
Come on, Susanna.
You know you want to.
Temperature, moisture, food source,
pH.
and oxygen. It's crazy. It's showing my age. So those three things, if oxygen's over 21%, moisture over 22, temperature 5 to 35 Celsius, decay will happen. Well, you can take a clean piece of wood and put it in that environment and it'll decay. So people have got this place off the coast of New York. It's called Treat Island. Treat, T-R-E-A-T, Treat Island. And this island is where they do all kinds of treatment tests. And what they did one time is they took two sawhorses. They took a treated piece of wood and an untreated piece of wood. They put them on the two sawhorses. They put a vertical spike in the treated one and a vertical spike in the untreated one. Which one do you suppose lasted the longest? Anybody want to put their hands up? Which do you think lasted the longest, the treated one or the untreated one? Neither of them. They both decayed the same time. Why? Because I took a vertical fastener and put it into the bright wood from the top. The water follows the vertical fastener to the bright wood, and it doesn't matter if it's treated on the outside or not. So if I buy expensive treated wood and I put vertical fasteners from the top in through the treatment, it's going to decay inside.
Dan, I think we've got to let people go. The people from Europe, it must be Lisa and Tobias in Sweden. It must be getting close to midnight.
Yes. Yeah. Well, I'm the perfect thing to put you to sleep. I'm just like a sleeping pill. Listening to me will just put you out. You can just go to bed right now. You're done.
No, it's not what I was going to say. I was going to say the next time we get you on, we're going to have to, get you started earlier. Yeah, because this has been great. This has been about 10 subjects in one. So thank you so much.
No problem. Thanks for listening to me.
Thank you from on behalf of everybody else that's also saying thank you and amazing. Let's make sure I capture this chat. There we go. Saved the chat. So until the next time, until next week, guys. Hopefully we'll all see you back on Vincent's presentation. We've got Wilmot out, who's a archaeobotanist from the Netherlands, going to be talking about charcoal. And we'll see you here as well, and coming from Canada next month. Hopefully, I think we've got somebody to talk about the log cabin they're building. Thanks very much. Okay, those in Europe, you can go to bed now.
Yes, thanks, guys. Appreciate you
Thanks
putting up with me.